Here's an engineering puzzle. You need to build an aerial system that can strike targets 1,000 kilometers away. You have limited manufacturing capability. You can't acquire advanced foreign technology openly. Your budget is a fraction of what your potential adversaries spend. Most engineers would say it's impossible. But between 2010 and 2024, one country solved this puzzle, not with one perfect machine, but with a system of imperfect, specialized machines working together. This is the engineering story of how Iran built a drone ecosystem under extreme constraints and what it teaches us about designing complex systems when resources are scarce.
Welcome to SciCuriousID, where curiosity meets science.
Part 1. The constraint problem. Every engineering project starts with constraints. Iran's were particularly severe. Constraint 1. No air superiority. Traditional military doctrine says, control the skies first, then strike. But Iran couldn't build world-class fighter jets. Sanctions blocked access to modern avionics, engines, and materials. Constraint 2. Limited precision manufacturing. Building one perfect stealth drone requires carbon fiber facilities, precision machining, and advanced composites. Building 100 acceptable drones requires simpler manufacturing, different problem, different solution. Constraint 3. Cost-asymmetry. A single F-35 costs $80 million. A single Patriot missile costs $3.5 million. Iran's entire annual defense budget is roughly $25 billion. You can't win by playing the same game. The engineering question. How do you deliver military effect when you can't compete on quality, speed, or sophistication? The answer lies in a classic systems engineering principle: when you can't optimize for peak performance, optimize for the system's overall effectiveness. This means accepting trade-offs that seem counterintuitive. Part 2. The systems solution. Iranian engineers didn't build one drone to do everything. They built a layered architecture. 3 distinct layers, each optimized for different functions, each compensating for the other's limitations. Think of it like a 3-tier computing system. Edge layer. Fast, cheap, disposable, the Kamikaze drones. Middle layer. Persistent, observing, connecting, the tactical drones. Top layer. Strategic, long-range, coordinating, the heavy endurance platforms. This is modular design applied to warfare. Instead of one expensive multi-role aircraft, you have many specialized units. The system as a whole becomes more resilient because losing one component doesn't collapse the entire capability. But here's where it gets interesting from an engineering perspective. None of these drones are particularly advanced individually. The innovation isn't in the components. It's in the system integration. Part 3. The supply chain reality. Before we examine each layer, we need to address how these were actually built, because this reveals another engineering constraint. Iranian drones aren't purely indigenous. When Ukrainian forces captured Shahd 136 drones and disassembled them, they found Western-made electronics, GPS modules, processors, communication chips, Chinese components, structural materials, subsystems, commercial off-the-shelf parts. This isn't cheating. This is supply chain engineering under sanctions. Iranian procurement networks established front companies in China, Turkey, and the UAE to acquire dual-use components, parts with civilian applications that don't trigger military export controls. The engineering insight. When you can't build everything yourself, you design systems that work with globally available components. This creates vulnerability but also resilience. It's similar to how a startup might build a product using available APIs rather than developing proprietary infrastructure. Part 4. The Kamikaze layer. Let's examine the most famous component, the Shahd 136. From an engineering standpoint, this is fascinatingly simple. It uses a piston engine, think lawnmower or small aircraft motor, cheap, widely available and fuel efficient. Wooden or composite wings, easy to manufacture and radar transparent. GPS navigation, commercial modules, not military grade. Pre-programmed flight paths, no real-time pilot, no complex communication links. The trade-offs: slow, 180 kilometers per hour, slower than a car on a highway. Loud, propeller engine audible from kilometers away. Not stealthy, radar cross-section is small but not invisible. Limited accuracy, GPS can be jammed, precision is meters, not centimeters. Why this design works? The Shard 136 accepts these limitations because it's designed for saturation, not precision strikes. If you launch 50 at a power plant, you don't need each one to hit a specific transformer. You need the system to ensure that 5 to 10 get through. This is redundancy engineering. Instead of one perfect weapon, you have many acceptable ones. The system probability of success increases with numbers, even as individual reliability is moderate. The cost? Estimated $20,000 to $50,000 per unit, compared to a single cruise missile at $1 to $2 million. Part 5. The tactical layer. The Kamikaze layer strikes, but someone needs to find targets and assess damage. That's the Modular 6 and a Babel 3. These are ISR platforms: intelligence, surveillance, reconnaissance. Think of them as flying sensors with weapons attached. Modular 6 engineering: 12-plus-hour endurance, precision-guided munitions under the wings, and beyond line-of-sight communication. Its role: find first, then strike. The Babel 3 is simpler and cheaper, used for pure reconnaissance or feeding data to Kamikaze drones for targeting updates. This is distributed warfare, no central command node, no single point of failure. From a network engineering perspective, this is a mesh network, resilient and harder to disrupt. Part 6. The strategic layer. For deep strikes and persistent presence, Iran developed the Shard 129 and Shard 149 Gaza. These are the heavy lifters, turboprop engines, high-efficiency design, and 24 to 35-hour endurance. The Shard 149 specifics: 35-hour flight time, 500-plus kilogram payload capacity, and satellite data links for global reach. These platforms can maintain continuous coverage of a region, creating a virtual presence that manned aircraft simply can't match without refueling. Notice the design philosophy: turboprop, not jet. Prioritizing endurance over speed. Accepting you'll never outrun a fighter jet, so don't try. Be everywhere at once instead. Part 7. The economics of interception. Now we reach the most interesting engineering analysis, the cost asymmetry that makes this system viable. The problem for defenders. A Shard 136 costs roughly $20,000 to $50,000. But intercepting it requires far more. A Patriot missile costs $3 to $5 million per shot. One missile for one low-cost drone. A fighter jet sortie costs over $10,000 per hour, plus the significant risk to the pilot. Even if you shoot down 90% of incoming drones, the 10% that get through cause damage. Meanwhile, you've spent millions defending against thousands. This is economic warfare engineering. The attacker's goal isn't just physical destruction, it's forcing the defender into unsustainable spending. But here's the critical engineering insight. This asymmetry cuts both ways. The system adapts. Ukraine developed countermeasures, electronic warfare. GPS jamming costs far less than missiles and forces drones off course. Then came Stinger drones, Ukrainian Kamikaze interceptors costing just $1,000 to $2,500 each. Fighting cheap with cheap. Part 8. The adaptation response. The most recent data from 2024 and 2025 shows this engineering cycle in action. The initial approach was mass launches of 50 to 200 shards to overwhelm defenses. But the defense evolved. Ukraine engineered distributed radar networks that are much harder to saturate or blind. By combining long-range missiles with adapted guns and electronic warfare, they achieved roughly 90% interception rates. The Pentagon's assessment: Iranian drones failed to give Russia significant advantages and suffered numerous failures on the battlefield. The Shard 136 limitations, GPS dependency and slow speed, became vulnerabilities once the threat model was understood. This is the Red Queen effect in engineering. You must keep evolving just to maintain your relative position. No advantage remains dominant forever. Part 9. The Systems Lesson. What can we learn from this as engineers and systems thinkers? Lesson 1. Constraints drive innovation. Iran couldn't build F-35s, so they built something else entirely. This is classic disruptive innovation theory applied to military systems. Lesson 2. Layered resilience beats monolithic performance. 3 mediocre systems working together often outperform one excellent system working alone. This applies far beyond warfare. Lesson 3. Cost is a design parameter. Engineering isn't just about maximizing capability, it's about optimizing capability per dollar. The Shard 136 is worse in every metric except cost effectiveness for saturation attacks. Lesson 4. Systems are temporary advantages. Iranian drone ecosystem worked brilliantly until defenses adapted. Sustainable advantage comes from rate of adaptation, not static superiority. Lesson 5. Supply chains are engineering architecture. You can't separate the physical design from the procurement network. Indigenous technology is rarely truly isolated. So the next time you see headlines about drone swarms or asymmetric warfare, remember, this isn't just about weapons. It's about how engineers solve problems when the obvious solutions are blocked. Iran's drone ecosystem is a case study in modular design over monolithic platforms and system integration over component excellence. These principles apply to any engineer working with constraints. The question is, what problems in your field could be solved by accepting different trade-offs? Sometimes the best engineering isn't about building the perfect machine. It's about building the right system of imperfect machines.
Thanks for watching SciCuriousID. Until next time.